go. All right, so getting back to here, arrays of structures. Well, there's really not much to say about it. You have done it already with your previous homework assignment. Multi-dimensional array, we can talk about it. It's pretty easy. It's just an array of an array. Okay, that's basically a multi-dimensional array. So what we'll do today is to kind of move forward a little bit. We'll talk about strings. We'll talk about pointer arithmetic, which is an interesting topic because it is relating pointers to arrays. In C and C++, a lot of times when you look at a pointer, you can look at it as an array and vice versa. Okay, so we'll talk about how that works. I expanded a little bit on the C strings section, so we can talk about it a little bit too. And as a shorthand, okay, we have this little topic here for initializing an array. So we have all of these extra stuff that we can talk about related to arrays today. So let me just kind of go through the implementation of arrays first, just to make sure that we got everything done here. We talked about the allocation. So the allocation of an array, it's kind of like the allocation of any local variable, except in this case, you use square brackets to indicate how many elements do you want in this particular array. Other than that, it is the same thing as allocating storage for a single variable. We talked about pointers and arrays already. Basically, this is saying that X is quote-unquote an array, but we don't know the size of that array. Okay, it's not the same thing as an empty array. If you want an empty array, you put a 0 within the square brackets, which is pretty pointless. Okay, an empty array is just completely useless. So when we look at these two statements, they are really quite different. Without any further code, okay, if we just look at these two, without any further code, this is going to cause us trouble, whereas this is okay. Okay, so what we'll do is we'll take a look at these two declarations because I think we have not talked about this yet. Okay, this note has been up on Moodle for a while, but we haven't really talked about it. So we'll talk about the first one first. Okay, int x, and we have open and closed curly brackets right next to each other, but nothing else, nothing in between the square brackets. So the question is, from the perspective of the compiler, what does that mean? Okay. Well, to the compiler, this means exactly the same thing as int asterisk x. In other words, x is really just considered a pointer to an integer. And nothing more than that, okay? What exactly is a pointer? Can someone remind me what a pointer is? What does a pointer store? An address, okay? And if I just declare a local variable, what is the value of that local variable? Doesn't matter what type it is uninitialized, right? Okay, so let's go ahead and write a very simple program just to illustrate this point. Because seeing it happen, especially through GDB, is much more clear. It's much clearer than having me just to explain the concept. So we'll go ahead and write a program called array1.cpp, and we'll just go ahead and write exactly what I have in my notes. So the first one is int x and then open and close curly braces. It's a valid syntax, okay? It basically says x is an array, but we don't know where the array is. It has to be initialized. And then the second one is int y, and then we put 10 within the square brackets. This is different. This is saying that y is an array of 10 elements. So the storage for the array is initialized for y, but there's no storage, there's no array allocated for x. X is just saying, hey, somebody's going to tell me which array I'll be pointing to, but at this point, I'm just a pointer. I don't know where I'm supposed to point to. I'm uninitialized, okay? And that would be the entire program. Well, let's go ahead and throw in the other stuff too. So I want to initialize the first, quote-unquote, first element of x to 0. We'll go ahead and try to initialize the first element of y to also 0. So I'm just putting in exactly the same code as in my sample code here in the notes. And then we'll compile this program, and then we'll run it just to see what happens. Okay. I will turn off warn all, for the time being, okay, just so that we can see that, oh, it does compile, okay. But when I turn on the warn all, you will see that the compiler will complain about and say, hey, this is not right. Okay, so this is just a compile, and it does not, oh, it won't even let me do it. So if it's not, storage size of X is not known. Okay, so when you declare a local variable, it won't let you do it that way, which is great. Okay, this is not, this is just not allowed. I'm going to try something a little bit different and see if it works as a C program, because this may be a C versus C++ kind of thing. So I'm going to try this again, but this time using just a regular C program, and it does not let me do it either. Okay, that's good. Okay, so we don't have to worry about this type of thing, because you can use it as a parameter. Okay, when you use it as a parameter, it means it's just a pointer, but you cannot use it to declare a local variable, which is good. Okay, the other thing is there's no index bound checking when you're dealing with arrays. So when you declare y to be an array of 10 elements, 10 integers, there's nothing preventing you from doing this. Okay, which element is it addressing? The line that I'm highlighting here. It's not the 10th, it is the 11th. Okay, because we count from 0. So there's y bracket 0 being quote unquote the first, y bracket 1 being the second. So by the time we go to y bracket 10, it is actually the 11th element. But the compiler will not complain about this. And during runtime, you will get something that is kind of funny. Okay, so what we'll do is we're going to try this out just to find out what's going to happen. So we'll write a second program, array2.cpp, and we have y as an array of 10 integers, just like before. And this time I'm going to put an x here, which is just a regular integer. I put a z here, which is just a regular integer. And then we'll say x equals 2, z equals 20. And we'll have y bracket 10, which should not exist. Okay, we'll say this is 5. Okay, everything else is uninitialized. So we want to find out exactly what's going to happen when we compile this program, and also when we run this program. Turn 0 at the bottom here. So g++ dash warn all dash c array2.cpp. It complains about certain things, but this time I did not get any errors. These warnings are not, what you would expect it to warn you about, because all of these warnings are just saying, okay, this particular variable is initialized, set, but it's not used. Okay, it's just questioning, why would you bother to create a variable, put a value into it, but not use it anywhere in the program? That's what it's complaining about. But it's not complaining about, hey, y only has got 10 elements. What are you doing with the quote-unquote 11th element, which does not exist, which is the most crucial problem with this particular program. So now we'll go ahead and link the program, g++-o to link array2.cpp, and then we'll use GDB to actually run the program. I forgot to use a -o for the linking. There we go. When we compile, I forgot to specify -g to include GDB debug information. We have to relink and go back to GDB. There we go. Okay, so we'll put a breakpoint on line 7 and run the program. Now we're on line 7. Line 7 is pretty easy stuff. Okay, we have a local variable x, and this should initialize its value to 2. I already know that. Okay, so this is not a main issue. What I do want to know, which does not seem to make much sense, is where is x? Well, x is at this particular address. Okay, fine, we'll just take note of it. In fact, I'm going to make my screen a little bit larger so we can keep track of more information without having to scroll. Single step, Okay, this is the next one initializes z, and we'll go ahead and do the same thing. Where is z? Okay, it is at A0 instead of A4, and we'll single step through this. And now we'll go ahead and say, hey, where is y? Y is over here. So you can see, okay, where is y relative to x and y? I mean, x and z. Which one is before which other ones? Look at the addresses. Just look at the least two significant digits. All you have to do is to compare 7 to 8. Which one is a smaller value? 7 is smaller. Okay, so the array is actually quote unquote before both single or individual variables. Okay. All right. And remember, you can also do something like this. You can say, where is the first element of the entire array? What do you think that would be? What do you think this GDB is going to print when you ask, hey, where is the first element? Same address as the entire array. Okay, that makes sense, right? Because you basically have a box of items. So the location of the first item of the entire box is the location of the box itself. Okay. So when you press Enter key, hey, that works out. Okay. So from this, can anyone kind of just kind of guess where is y bracket 10? What is the address of y bracket 10? The math is fairly easy, right? So the math is basically 0xBFFF F978, which is a hexadecimal number because of the 0x. But let's just say that we can deal with base conversion using a calculator. GDB can do all the base conversion stuff, so I'm not too concerned about that. Okay. Each element has 4 bytes, right? The first element is at an offset of what from the beginning of the entire array? You're looking at it. 0. Okay. So that means the 10th or the 11th element has an offset of how many bytes from the beginning? Well, each item has 4 bytes. 40, right? Okay. So, but this 40 is in decimal. So since I have this number in hexadecimal, I better change the number 40 into hexadecimal first. Can someone do a quick math and tell me what is the hexadecimal or base 16 representation of the value 40? How many 16 do we have in 40? 2 with a remainder of, yep, then it's 28. Okay, 28 in hexadecimal is 40 in decimal. Okay, so we are now going to do addition in not base 10, but in hexadecimal, in base 16. 8 plus 8 is 16 in decimal. But in base 16, what is 16? F is 15. In other words, I'm asking you what is 5 plus 5 in base 10. It's represented as 1 0, okay, or a 0 with a carry. Okay, so that's what we'll do. 8 plus 8 is a 0 with a carry. So now we have 7 plus 2 plus 1. 7 plus 2 is 9. 9 plus 1 is 10. But it's only 10 in base 10. Okay? In base 16, how do we represent the value of 10? A, lowercase a, or uppercase a, depending. And the rest is not impacted because there's no carry coming out of the second column. So the rest we can just kind of copy, right? There we go. All right. So this is the address of what again? Y bracket 10. But we have seen this before. Who also has the same address? Z has the same address. Okay, great. So now we have the quote-unquote 11th element of Y and the individual variable Z having the same address, which means if you change one, quote-unquote, the other one would also change. Because what we have now is not 2 distinct items. We have 2 ways to refer to the same location in memory. That is what we have here. So that means at this point, if I execute this instruction or this line here, which is changing Y bracket 10 to 5, I should change Z to 5. Okay. So before we do that, let's go ahead and take a look at the value of z. It is 20, which is exactly what I expected because I ran this particular statement already. Now I'm about to run this particular statement, which is changing the quote-unquote 11th element of y to 5. Single step, print y bracket 10. Hey, that's 5. Well, that's exactly what we would expect. What about z? It should be 5 as well. And this is where you say, holy moly, okay? And this is the sort of thing that you can only do in C and C++. You cannot do this in Visual Basic. You cannot do this in Java. You cannot do this in Python, Perl, or any other programming language. C is the only program, C and C++ are the only two languages where this kind of problem can happen. Okay, does everybody understand or see that we have a problem here? Yep, go ahead.
How do we avoid this?
How do we avoid this? By being very careful. C and C++ are programming languages that were, okay, so to understand why we have a problem like this, what you need to do is to look into the history of C and just C, okay, because the history of C language is kind of important because, you know, I know this is not a history class and you know, that part should not be important, but in order to understand why we have some really kind of weird features of C, it is important to understand, you know, how it came about, okay? It's designed by Dennis Ritchie, and who passed away within a week or maybe a week before Steve Jobs passed away, okay? But nobody knew when he passed away. When Steve Jobs passed away, everybody went like, oh man, what a loss. You know, the computer industry has lost a great talent. But nobody understood that Dennis Ritchie was the person who not only wrote the C programming language, but also developed Unix to begin with. And then when you use iOS, you know, or when you use a Mac OS X, what do you think is underneath the hood?
Unix.
It's all Unix. So without Dennis Ritchie, you know, Apple products definitely would not be the way they are now. Okay. Is it that boring? Okay, so history, early development. And this is Thompson, and this is Ritchie. They're exactly what you would expect, you know, as, you know, computer scientists coming from the 60s. I mean, you know, if you look at Stallman, okay, you know, Richard Stallman, he is still looking like that today. He is the, okay, since we are on that topic, Richard Stallman. See, that's Richard Stallman right here. And if you compare how he looks right now to how these two guys looked, you know, back in the days, hey, I think there's a certain similarity. I mean, they're not exactly the same person, but, you know. Okay, the origin of C is closely tied to the development of the Unix operating system, blah, 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 blah. Originally implemented in assembly language on the PDB-7 architecture. Okay, so that part is not important. The architecture, the PDB-7, you know, is not important. The important part is he was originally writing the operating system in assembly language. Now, what is assembly language? Well, since you have to take this class before you take cisp 310, obviously most people in this class do not know what is assembly language programming. But I can give you an analogy. Using C to write a program is like going to Home Depot, okay? You get a whole bunch of 4x4s, 2x4s, you know, planks and whatnot, and you just put things together, okay? So you have some basic structured building material, and you can do stuff with it, okay? Writing programs in assembly language is kind of like, okay, here's a tree trunk, do something with it. This is a chunk of tree, okay? A chunk of a branch, okay? And here's some sand, do something with it, okay? It's really raw, okay? In order to build a house using, you know, that kind of raw material, so instead of having a slab of marble or, whatever material that you want to use in the kitchen on the sink, you are just given a big chunk of a rock. Okay, you have to cut it down, polish it, and do all kinds of other work to prepare it so that it can be used for construction. So, and understandably, these guys were kind of bored by doing all the chore stuff of writing a program. The other analogy is you're trying to build a castle, but the material that you have is basically individual grains of sand. So you're trying to build a castle, not a sand castle, a real one, using a pair of tweezers, and you're just trying to glue individual grains of sand on top of each other. That is assembly language programming, and I can see how much you guys are looking forward to cisp310 at this point. So these two guys were absolutely bored by writing the operating system in assembly, and what they did was they invented the B language, which is down here a little bit, right here. So they invented the quote-unquote B language, and of course if you go to the link here, it explains why it is called a B language. It's derived from BCPL or before C programming language. It is possible, okay, so this is just a theory that the name is based on Bond, an earlier but unrelated but rather different programming language that Thomson designed for use on Multics. And if you look at the name Multics, it is the name of another operating system as opposed to Unix. Multi, uni, yep.
So this programming language was named BCPL before C was around?
Before C is around, yes.
And it was called before C programming language?
That's one way to interpret BCPL.
Oh, okay.
So it's actually a basic combined programming language. But some people understand it now as the before C programming language because it is the predecessor of C. It's kind of like PHP as an acronym has no actual definite definition. Does anyone know what is PHP? What does PHP stand for? It changes over time. So that acronym actually does not have a definition. But anyway, getting back to the origin of C. So so these two guys, Ritchie is the principal person who invented the C programming language. So anyway, so this is a programming language. It's designed by a very high-level, experienced programmer for himself. It's kind of like a tool that a contractor will conjure up at a job site and say, you know what, I'm really getting sick and tired of having to do this and realign stuff, all day long. I'm going to make my own tool just to, make this part easier to do. Okay, was that tool ever invented to be sold at Home Depot? No. So as a result, it was lack certain things, right? What do you think that tool is going to lack compared to a tool that you can buy at Home Depot or Walmart? Safety features, exactly. Okay, so by this very historical reason, C and C++, they do not have safeties. Okay, I'm not sure how many of you deal with firearm and stuff like that. Okay, this is kind of like the kind of gun that has no safety and no safety features whatsoever. The whole thing is designed to shoot well, and that's it. Okay, it's also equivalent to a tool that has no shield, no safety feature whatsoever, because that's just weighing down the tool. Why do we need all this tool, shield and whatnot? I know how to use this tool correctly. Well, but not your usual Home Depot shopper, which will be you guys. Students learning how to write programs. You guys can benefit from safety features. But C has no safety features. And that's why we can do this. Okay? That's why there's no boundary check when you access elements in an array. Are we still doing okay so far with this concept? So you have to be careful. When you write programs in C and C++, you are responsible to avoid problems like this. Okay? And later on today, hopefully we'll get to that part. We'll also explain, what kind of bad problems can come up when people do this kind of thing. Okay. So just moving on, it keeps going on and on. to involving x and y. Okay, that's not. Arrays is an extension of pointers. Okay, so I'm skipping a whole bunch of sections there because the x being an empty array doesn't actually work. We cannot make that happen. Array is an extension of pointers. In other words, every single pointer is quote unquote an array. But it's not the same kind of array as a declared array. So what I'll do is I'm going to go back to the program that we had earlier, which is array 1. And we'll change this program to, because this is not actually valid syntax, we'll change it to just a pointer. Okay, I'm hoping by now most of you recognize the asterisk symbol when you declare a variable means it is a pointer. So on line 3, it is saying that x is a pointer to an integer. You have to kind of read it backwards. Okay, so you read the x first, and then you read the asterisk, and you say x is a pointer to, and then the type of things that they point to is the last one. So we kind of know what a pointer is. It is supposed to store the address of an integer in this case. Without initializing x, we can actually, line 7 syntactically is correct. Okay, it's not going to do anything that is correct or useful, but it is syntactically correct. So the first thing we do is we will just go ahead and I'm going to copy this one back to array1.cpp. So I'm not going to use warn all. I will just go ahead and compile with gdb debug information. And you can see G++ does not complain about it at all. Okay, it's all good. So let's go ahead and link the program. Oh, let's recompile this time, but we'll specify warn all. What do you think the compiler is going to complain about this time? Well, the set but not used thing is going to happen. Okay, that's the usual thing. We already know about that one. What else do you think the compiler will complain about? Sorry?
Maybe a pointer is not initialized?
Exactly, it is not initialized. I think it will refer to it as, a variable is used but not initialized, or something along that line. Okay, so we'll take a look. And it says it complains right here, x is used uninitialized in this function. So that's basically what you said. Okay, that's because we are using x as a pointer before we actually store any usable address in it. Are we still doing okay so far? What do you think is going to happen when we run this program, when we actually execute the program? What can potentially happen? Now x is uninitialized. Let's go back to the program so we can see what we are talking about. All right, so look at line 7. When you look at line 7, it's basically saying, let's go ahead and treat x, which is a pointer, and uninitialized, as an address of an array. And we're trying to access, in this case, the first element. I can change that 0 to 1, 2, or whatever number. Okay, it doesn't matter. But I'm still trying to utilize a pointer, which is supposed to store an address, and I'm trying to use that address as the first element of an entire array. But do you see me updating or initializing x here? Wait, but what about line 7? Line 7 is doing something about x. What is it initializing? Is it initializing x, or is it initializing where x is pointing to? Where x is pointing to, okay? So I'm still using a uninitialized pointer on line 7, and that's why we might have a problem. If a pointer, like an integer, is uninitialized, what is the quote-unquote value in that uninitialized local variable?
It's garbage.
Arbitrary, right? It's garbage, it's arbitrary, it is unknown. We know it has 32 bits, but we have no idea of what zeros and ones will be in it, okay? So as a result, we're going to treat an unknown bit pattern, 32-bit wide, as if it is an address. And we say, okay, treat this as an address and go there and store something at that location. Okay? With 32 bits, we can specify 4 billion locations, well, a little more than 4 billion locations. And out of those 4 billion locations, only I would say maybe megabytes of those are actually accessible to your programs. In other words, less than 1% of all of those potential addresses is actually something that your program can do something about. The rest is, if you try to access any location that your program is not supposed to go to, what do you get? A segmentation fault, okay, which is a crash, okay? So this program may end up with a crash, okay, but it all depends on what is the uninitialized value of x. That is the key, is we don't know what it is, okay? So it might crash, it might not crash. Crashing is the best thing you can hope for. Why do you think I said that? I mean, why would I be saying, if this program crashes on line 7, it's the best thing that can happen?
Because it definitively tells you what's wrong.
Exactly, where the problem is. Instead of having line 7 not to crash because for whatever reason that location in memory just so happens to have a valid address, whose address would that be? We have no idea. So it's just going to randomly corrupt something, not give you any warning, not crashing at the place where the problem is, and then somewhere down the road it's gonna crash. It's gonna do something that's wrong. That would be much worse. Okay. To give you an analogy, it is kind of the same thing as when your engine overheats or has a problem. Not only do you get a check engine light, but it will actually shut down. Okay, your engine will just kind of shut down. Your transmission will go into neutral, so your car can coast to a stop. Okay, and say, okay, I'm in trouble. I'm not gonna do anything at this point. Okay, I need a mechanic to take a look at this. Instead, what C is going to do is like, that's nothing. So when your engine overheats, it doesn't give you any warnings. You don't see anything. And the first sign that something is wrong is when your regular internal combustion engine turns into a steam engine. You see all that steam coming out of your hood. That's the first sign of trouble. Does that tell you anything about why it happened? No, it just tells you that, well, you better not drive the car anymore because you cannot see past your windshield because of all that steam and all the coolants, splashing onto your windshield. That would not be a drivable condition. Okay, so what we'll do is we'll actually go ahead and run this program and see what happens. We did a compile, and now we'll do the linking. Array1.o, gdb array1. Put a breakpoint on line 7. Line 7 is the line where the problem is. So we run the program. The first thing we do is we want to say, oh, tell me where's y. Okay, y is an array, but where is it? It has a definite location, has values. They're uninitialized, but nonetheless, okay, it is somewhere in memory. Tell me where is x. The location of x is not a problem. Okay. Because this is the address of a pointer itself. The pointer is declared, it has a space to live. That is not a problem. It's the content of x that is a problem. In other words, if I say, hey, where's x? Or what address is x storing? For whatever reason, okay, it is storing an address of 0. The location 0 is not a place where your code can access. So anytime you try to overwrite that location, or anytime you try to read from that location, a segmentation fault is going to happen. So when I single step this program, it gives me a segmentation fault, okay, which is great, okay, because it crashes where the problem is, instead of just randomly corrupting some other locations and causing issues down the line. Are there any questions about this particular program? Yep.
So we had x 0 in square brackets equals 0. What if it was x1 in square brackets equals 0?
If you use an x bracket 1, then it will be accessing location 4. Okay, because you can still do it like this. You can ask theoretically, where is x bracket 1? Okay, and it will tell you it is at location 4. Because x is storing an address. which I'm treating as the beginning of an entire array. Is that okay? So when you look at the entire array, it is starting at location 0. But everything in this array is 4 bytes long. So the address of the second thing in the array should be 4 bytes away from the beginning of the entire array, and therefore it is at location 4. But if you try to overwrite, x bracket 1, it will crash again because location 4 is also a location where you cannot access. All right. Are there any other questions about this program? Any questions? Okay. So we go back to the program, and this time we'll fix it. We'll initialize x first. So one way to initialize x is simply to say, hey, x, go ahead and store the address of y. That's perfectly okay. Because what we are saying is, hey, x is now storing the address of y, and y is an array. It does have 10 integers allocated, so now it'll be okay. But it will just make x and y being exactly the same thing. X bracket 0 will access the very same thing as y bracket 0. Is everybody okay with this code here?
Is there any other way that you can do this or not? Are there any other ways that you can do this or not?
Are there any other ways to do this? Oh yeah, there are many other ways to do the same thing. Instead of saying, where's y, you can say, hey, give me the address of the first element of y. That would do exactly the same thing. Yep.
So if you were to just print the value of y without any brackets, that would print the memory location that the array starts at?
That is well, that's a good question. Okay, that's something that I did a little bit earlier, and okay, let me just do this first. So I'm just recompiling and relinking the program. And this time we will put the breakpoint at the same place. So if you print x, it is saying that x is a pointer, and right now before we initialize it, it is storing an address of 0.
What about just y though?
If you do it with just y, it is different. It gives you the actual values of the individual elements of y. That is because in the scope of main, y is known as an array of 10 integers.
Okay.
So the compiler does keep track of that information, but when you do the indexing, it does not use that information to check and say, hey, you're trying to access the 11th element, it does not exist. Okay, that's a good question. All right, so when we single step, okay, what I did was I just executed this instruction here. So now when I print x, it has a particular address in it. But when you look at the address of y, it's the same thing. Is that okay so far? But when you look at the address of y, you'll note how x is different from the address of y. X, when you say x, it's simply saying, this is a pointer to an integer. That's all it says, okay? It is a pointer to a integer. But we print ampersand y, which is when we print the address of y, it says, hey, this is the address, but what is the address, what is it an address of, okay? It says it is an address of 10 integers. Okay, so it's a little bit different because in this context, y is an array of 10 items. So from here on, x bracket 0 is the same thing as y bracket 0, and so on. Okay, x and y x is basically an alias of y from here on. Are we doing okay so far with this? Is that okay? All right. So if this is okay, we're going to throw a range into this whole thing. So instead of saying x is the address of y bracket 0, now we'll say, well, can we do something like that? In other words, x is now the address of the 5th element of y. Well, nothing says you cannot do that because y bracket 4 is an integer, and x is a pointer or the address of an integer. So nothing prevents you to say that, hey, I want x to store the address of the 5th element of an array. That is okay because it is still the address of an integer. Are we doing okay so far? But then what is x bracket 0 then? So what we have here is a situation that looks like this, okay? So y is static, okay? In other words, y has a certain number of elements in it. In this case, we have exactly 10 elements in y, okay? And you cannot change y, cannot change y to point to some other array. It is just set over here. But what we have here is this is y bracket 0, y bracket 1, 2, 3, 4, 5, 6, 7, 8, 9. We extracted the address of the fifth element of y, and we say, hey, I want x to point to this location, which is perfectly okay. But every time you have a pointer to an integer, that pointer can be seen as an array. So when you say x bracket 0, it would be pointing to the same thing as y bracket 4. What about x bracket 3? What do you think that would be equivalent to? Okay, let's find out. This is x bracket 1, x bracket 2, x bracket 3 is the same as y bracket 7. Okay? And once again, this is something that you can only do in C and C++. No other programming languages would let you do something like this crazy. Yep.
Is this something that ends up being useful? Like the fact that C++ can do that, is that something that's used?
Well, it is useful once you pass an array as a parameter to a subroutine. It does not. It will have lost the. This is an array of 10 elements. That part would be lost completely.
Okay.
So you end up only using pointers once you're in a subroutine that has a parameter that is a pointer. So there's no such thing as passing an array around in C and C++. You're only passing a pointer around. So whether it's useful or not, I'm not sure, but this is the only way you can pass an array to a subroutine. Yep. We're not inside, we're not passing it as a parameter to a subroutine yet, so we are not. So in this case, it's really just going like, oh, okay, so that is the same thing. Okay. But just to double check, what we'll do is we'll go ahead and run this program and double check, what we observed or what we thought, would be. I'm just gonna use 525 and 526, and then we'll GDB the program again. Put a breakpoint on line 7. Run the program, single step. So now we can say, hey, tell me what is x. Tell me what is y bracket 4, or what is the address of y bracket 4. Okay, fine. This is to be expected, because after all, I said, hey, give me the address of y bracket 4 and store that address into x. And there's no reason why x and the address of y bracket 4 should not be the same at this point. Okay, but remember what I was asking in class. What exactly is x bracket 3? Is it really the same thing as y bracket 7? That was the question, right? So we can verify this in two ways. The first one is not as good as the second. So the first thing we can ask is, tell me whether x bracket 3 has the same value as y bracket 7. You can ask that question. Any syntax you can use in a regular C and C++ program, you can use it as part of the expression of print in GDB, which is really handy. Okay, if you think about it, this is really, really handy. So you can ask that question, and we'll press the enter key, and it says it's true. Okay, that's kind of expected, but it is not definitive, because it is possible that the entire array of y has the same value. Okay, so this by itself is not really telling you that x bracket 3 is an alias of y bracket 7. To know that they are actually aliases of each other, you can now compare the addresses. This is also something new. Okay, we haven't seen this before. We did not know that we can actually compare not only integer values, but we can also compare addresses. You can say, okay, here's the address of something, here's the address of something else. Are they the same? We can ask that question. And the answer is yes, they are in fact the same. Are we still doing okay so far with all this fun stuff? Okay. Hey, if we can compare pointers, can we do addition and subtraction with pointers? Seems to make sense, right? Okay. It's kind of like saying, okay, here's the address of tax house. Okay. Then you can say, what is the address of 3 houses down the street? That seems to make sense, right? Or you can say, this is the street number of tax house. This is the street number of another house of the same street. How many houses are between tax house and this street address here? That seems to be a valid question to ask. Is that okay? So all that stuff is actually either here or somewhere else. I think it is here. Okay, so this is the first part that makes things kind of go like, okay, that's kind of weird, but it is true. Okay, the address of PTR bracket E. Okay, so here your PTR is a pointer of something, and E is an expression that evaluates to an integer. This is really the same thing as PTR plus E. In other words, the address of the element E of the array pointed to by PTR can be expressed as PTR plus E. PTR being the pointer itself, E being an integer like 0, 1, 2, 3, and whatnot. Okay, it's the same thing. What if you're not interested in the address and you're interested in the content of that particular element? So PTR bracket E without the ampersand, which is the value of the element, is the same thing as dereferencing PTR plus E. That is kind of strange, right? So let's go ahead and check whether that actually works or not. Okay, so we'll go ahead and redo the program a little bit here. Now you can do all of this stuff in GDB too. So let me just kind of show you how to do it in GDB first, and then we can go back and finish the program. So let's put a breakpoint on line 7, run the program, and stop here. Okay. So we have just run, we just ran line 7. So X is now the address of Y bracket 4. Okay. So what we'll do is we'll do the same thing as last time, just so that we kind of remember what we did previously. So we say, is the address of X bracket 0, is that the same thing as the address of Y bracket 4? Oops. The answer is true. Okay, not a problem. So now we will try the alternative syntax. Okay, so here we have X being a pointer, we have 0 being the expression E, and we have the ampersand, right? So if I want to fit this into the template of what is highlighted behind the command line interface, what should I type here? What is my pointer?
X plus 0.
X plus 0. Okay, and it is true. Maybe it is something special about the 0 here. Let's try something else. What about Y plus 4? It's the same thing. So when you add an integer to a pointer, what it is really doing is it's saying, oh, here's a pointer to one thing. When you say, a pointer plus 1, it is saying, oh, what is the address of the pointer? What is the next thing? That's basically plus 1 is the next thing, plus 2 is 2 things after that, plus 3 is 3 things after that. But that one thing, the size of that one thing, depends on what the pointer is pointing to. In this case, the pointer is pointing to an integer, so each thing has 4 bytes. So the next thing is 4 bytes away, the 2 things away is going to be 8 bytes away, and so on. Okay. And we can check that too, because what we can do is instead of checking for equality, we can ask specifically, what is this? And then we can ask, what is this? Okay. Well, we can also, excuse me, should be that. Okay. Wait, no, I'm not asking about the address of the pointer. I'm asking what the pointer is pointing to. So that's why I have to say print X and not print ampersand X. Okay. Now we can say, what is that. Okay, now this can be confusing because x is a pointer. It points to something blah 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 9, 8c. But when you look at x plus 1, you would think that it should point to 9, 8d, right? Because you're plus 1, c plus 1 is d. But no, it points to 990. And that's because each thing that x points to takes up 4 bytes. When you add 1 to a pointer, you're asking what is the address of the next item. And because each item takes up 4 bytes, the address of the next item is 4 bytes away from where x is pointing to. Is this part okay? Sort of? Okay, so this is called pointer arithmetic, okay? Things that you can do with pointers. And addresses. Well, if I can do something like that, do you think I can do something like this? Can we do subtraction? Since we can do addition, subtraction seems to make sense, right? Okay. In fact, I need to reverse this because x is the one that has a later or higher address, and y is the one that has an earlier address. What do you think that will give you?
The number of bytes difference.
Hmm?
The number of bytes difference.
The number of bytes, but remember it's typed, so x is a pointer to integers, y is an array of integers. So it's going to do the measurement not in bytes, but in number of integers in between. So you got most of the answer correct, except for it is not measuring in bytes, it is measuring in units of what the pointer points to. And because x is a pointer pointing to an integer, it will tell you how many integers fit between where x points to and where y points to. And how many do you think there is? Well, if you look at this, 0, 1. If x is here, it will be 0. So we have exactly 4 items between where x points to and where y points to. Okay. Let's press the enter key and find it. That's exactly 4. Which is great. Okay, this is pointer arithmetic that you can do in C and C++. Well, if I can do a subtraction, y minus x minus y is 4. Do you think I can compare? Just comparing x and y. Well, we did some comparison before already, right? We checked for equality, but now do you think I can check for less than and greater than all the other things that you can usually do with integers? Well, I'll let you guys decide whether that is true or not. Should that be true?
Yeah. Yes.
X has a higher address, so x is greater than y is definitely true. But this will be false because x is not a higher address compared to y. Is that still okay so far? Okay. And once again, with these pointer things, once again, it is only something you can do in C and C++, not in any other programming language that I know of. Okay. Are there any other questions about this? No other questions? Okay, so it's one thing to look at all of these statements and go like, oh, okay, it's kind of cool that we can do this. What is the application of doing something like this? Okay, so we want to write some programs and illustrate, why this might be useful. Okay, so what we'll do is we are going to go to the C strings. Okay, I extended this particular topic a little bit. I talked about how to read into a string, which is really just looking up the man page of some subroutines. So I'm going to skip it a little bit here. String processing as the root of all evil. I don't think I have covered this one yet. Have I? No? Okay. So let's talk about this one. We kind of have some understanding of arrays already. We kind of have some understanding of pointers. We also have some understanding about a pointer does not tell you where is the end of an array. Is that okay? We also have some understanding of what is a C string. Where does a string end? What is the indication that, oh, here's the end of a string? We talked about that last Wednesday. Null terminator, okay, which is basically just a byte with a value of 0. Okay, so that is basically a stop marker and say, okay, the content of this string stops here. So the big question is, what if you declare an array of size, let's say 32, but none of those bytes, none of those 32 bytes has a 0? Where's the end of the string then? It keeps going until there is a 0. Okay, does everybody kind of just get the sense of what I'm talking about, or not? Okay, I'll give you a particular program as a sample. Okay, switch back here, and before we go there, I will display a man page of string length. String length is a very simple subroutine. Okay, all it does is to tell you how many characters is in a string. Okay, when you read the description, it tells you that it makes use of the null terminator. Okay, so right here, the string length function calculates the length of a string, which is basically just an array of characters pointed to by the parameter s here, excluding the terminating null byte. Okay. So are we okay with the definition of the string length function, what it does? Are there any questions about this particular man page? Okay, all right, sounds pretty simple, right? Okay, so we'll go ahead and test string length with a few programs. So we'll go ahead and say str1.cpp. And if you want to use any of the string functions, you will have to pound include string.h. So it shows you, in the synopsis, it shows you what include file, what header file you have to include in order to use it. So string.h is the header file that we have to pound include. And what we'll do is we'll just go like, let's go ahead and declare an array called name, and we'll give it like, I don't know, 128 characters. Okay, which is a lot. Okay, so what this is doing is it is allocating 128 bytes as an array, and we call that array name. What is the content of this array?
Arbitrary.
It's uninitialized, arbitrary, unknown. All of those. They all describe the actual content. Okay, so what I need to do first, okay, is to initialize it. So I'm going to say, oh, let's just spell out tag here. And since a C string is null terminated, that means the last one is going to be a 0 to indicate, hey, it stops right here. Even though we have the space to store up to 128 characters, the actual content is only 3 characters long. Is that okay? All right. So then we'll go ahead and declare another variable. Let's say x here, and we say x is the length of the string starting at name, and that's all we want to do. So what do you think x should be after line 12 executes? And it's excluding the null character, okay? So x should be 3, okay? Fairly straightforward here. So we'll go ahead and test it out and make sure this works, okay? So we'll say G++. I'm just going to do a little shortcut here. So instead of using a -C, I'm going to use a -O to create the executable directly. And this is a regular usual warning, no big deal. GDB str1, put a breakpoint on line 8 just to illustrate the array is uninitialized to begin with. So if you say print name, it gives you a whole bunch of gibberish, okay? Well, that's only because it's uninitialized. And when it's uninitialized as an array of 128 bytes, it shows you all 128 bytes, okay? And it's all gibberish. When you see a backslash followed by 3 digits, like \371, something like this, the 371 is actually an octal number, base 8 number, indicating the actual bit pattern of that particular character. Okay. All right. So nothing too exciting here. Single step, single step, single step, and single step. When you say print name again, now we have the 3 characters that are properly initialized, as well as the null terminator. note the rest of the string is still garbage. Is that okay? Because out of 128 bytes, how many bytes did I actually change? 4. 3 plus the 1, the null terminator. Okay, but you guys got the idea. Now when I single step with line 12, I'm going to not single step but do a next, because if I single step, I'll be single stepping into string length, which is not something I can trace. But if I do an AND, which means I'm going to call the subroutine string length but not stopping in the subroutine, by this time x has a value of 3, which is hardly surprising. Okay, there are 3 characters before the null terminator. Are we doing okay so far with this? This is all good so far? Okay. So now I'm going to change the program a little bit. Instead of putting my name here, get rid of all that stuff, what I'm going to do is I will say, well, let's go ahead and initialize that using a for loop. So in this case, you can see how I is going to go from 0 to 127, which is the entire string. And I'm going to say each and every character is going to be, I don't know, pick something. Pick T here, okay, uppercase T. So what this is going to do is it will initialize the entire array of 128 bytes to the ASCII code of uppercase T. Well, in that case, where's the null terminator? It's not in the 128 bytes, right? So if there's no null terminator within the 128 bytes, what is string length going to do? Well, it will scan from the first byte of name, right? The first byte is obviously not a null terminator. The second one is not a null terminator. In fact, the entire name is not a null terminator. Will it stop at the end of name? Why can't it stop at the end of name? Because it doesn't know where it ends, right? So if string length doesn't know where is the quote-unquote end of name, what is it going to do when it is only looking for a null terminator? It keeps going. Okay, that's what it's going to do. Is it will keep going until it finds a null terminator, a byte that has a value of 0. And where do you think that is going to be? I have no idea. That's the whole point. I have no idea. So that means the only thing I know is x. If this program does not crash and it does come back with a number, that number is guaranteed to be more than or equal to 128. It might be just 128 if I'm lucky that whatever is following name as an array turns out to have a 0. Okay, it might happen, or it might even crash because nothing after name has a 0. That can happen too. I have no idea what is going to happen when I run this program. Do you want that to happen with your own programs, that you have no idea what is going to happen? Okay, so that means you have to be extra careful when you're dealing with strings, because if you end up with a situation like this, the program will behave in a way that you cannot even predict. So we'll go ahead and do a G++. Last time it complains about a little thing here, which is not a big deal. And we'll take a look. We'll put a breakpoint on line 12, okay? So put a breakpoint on line 12, run the program. I'm on line 12 right now. If I say print name, it's not an issue because it's just T repeated 128 times. So GDB is pretty smart not to print T exactly 128 times because nobody is going to count. Okay, so all it says is, okay, it's T, but repeated 128 times. Is that what we should be expecting? Yeah, absolutely. Not a problem, right? So when we type N, which is next, it will go ahead and call string length. In this case, it does not crash, which means it finds a 0, a byte of 0 somewhere. But where? Well, it turns out to be 5 bytes after the end, or 6 bytes after the end of name. Is that guaranteed to be always the case? Like 6 bytes after an array, there's always a 0? No. It just so happens to be the case in this particular case. Okay? Is that kind of a good thing or a bad thing that strings are treated this way? it can lead to really bad things. Okay. So here is a really quick introduction to Stack Overflow exploits. Okay, how many people have heard of that term, Stack Overflow exploit, or Heap Overflow exploit? No, nobody knows. Okay, you can look it up. You know, I can show you how to look it up. You know, I'm going to explain anyway, but I do want to show you that you can easily look up these terms: Stack Overflow exploit. Okay, or stack buffer overflow, doesn't matter, you know, it's all basically the same thing. Okay. All right, so in software, a stack buffer overflow or overrun occurs when a program writes to a memory address in the system's call stack outside of the intended data structure, yada, yada, yada. Okay, so what happens is all the variables, all the local variables live in a place that we call the stack. Okay. In this class, I will not go into detail to talk about what is the stack and what else is on the stack. Okay. But it is a place where all the variables are, all the local variables are, along with how a subroutine knows how to get back to whoever is calling it. Okay. So we'll just kind of look at one segment of memory in the stack and say, okay, this is where str is allocated. Okay, we allocated 128 bytes to the buffer or the character array, str. Okay, and you would say, but I will be so careful that I will never try to initialize an array out of its boundary. Well, that's good. Okay, but when you look up standards like TCP/IP and some of the graphics file standards, sometimes they also use the notion of null terminating a string. In other words, the comment of a particular graphics file may specify and say, you can type whatever you want, and this area will terminate with a null terminator, and you can only allocate up to 512 bytes. Okay, so there's definitely a size limitation, but on top of the size limitation, there's also a null terminator. Is that okay? So that means a properly formatted graphics file is going to contain up to 511 actual bytes of content plus that last null terminator. That would be the longest string you can store into the comment area of this particular file format. Is that okay so far? So when you are a programmer and you say that I need to process this particular graphics file, naturally you would say, I just need 512 bytes to read that particular section into my program for processing. That's okay. That by itself is not an issue. Okay? The question now is, how are you reading those bytes from the file into your program? Well, you say it's supposed to be null terminated. I could just read all 512 bytes, but since the actual comment can be only 3 bytes long or shorter, I don't want to waste all the time to read all these bytes, so I'm going to read until I see a null terminator. Okay, which makes sense too. What if someone is intentionally crafting a file to break your program? And look up the standard. The standard says it has to be null terminated up to 512 bytes, including the null terminator. So this really careful hacker, or this cracker, okay, there's a difference between a hacker and a cracker. So a cracker is someone who's intentionally trying to break something for malicious content, for malicious purposes. A hacker is simply someone who's using something out of the original intent. Okay, so an example of a hacker is turning a toaster oven into a wave soldering machine. There are people who do that. I would not use it for actually toasting bread anymore. Because of potential lead and other contaminant issues. But there are people who turn a toaster oven into a soldering equipment. Okay, that's hacking. Okay, it's simply using something other than what it was originally intended. A cracker is someone who's actually trying to break something for malicious purposes. Okay, so whoever is trying to crack your program is now going to say, let's see what happens when I specify a string that is, let's say, 5 kilobytes long, and there are no null terminators within the 5 kilobytes. So what you're looking at is something like this, okay? In a graphics file, which is basically just a long stream of zeros and ones, okay? One section here says up to 512 bytes can be here, and it will store a string that is null terminated. Somebody decides to mess around with your program and specify a string that is much longer than 512 bytes, and the null terminator is all the way here. Okay? In other words, within these 512 bytes, there are no null terminators. Okay? It keeps going until it gets to here. If your program uses the logic of I will keep reading from this file byte by byte until I see a null terminator, what is going to happen to the array string str512 on the stack? Well, it will fill it up, right? After it gets filled up, what's going to happen? It will start to overwrite other locations. In other words, if this is low memory address, and so lower on the whiteboard is lower memory addresses, it will start with this byte here, which is okay, not a problem. So you'll be basically filling up all 512 bytes. But because your program does not respect the actual length of the buffer, and you're just looking for a null terminator from the file, it will keep reading into quote-unquote this array until you actually find the null terminator. So after you fill up the entire str array, it will start to overwrite other locations on the stack. Okay? So all of this stuff here, whatever was originally here, would be quote-unquote corrupted. But it's not a random corruption. Okay? These bytes, okay, these bytes here that are not supposed to be there, they're not gibberish. Okay? The cracker will craft certain types of byte patterns here to try to get your program to do something that is useful to the cracker. So let's say this is a subroutine in the GDI plus library of Windows. Okay, and when you're dealing with a library subroutine of Windows, it means sometimes, maybe not all the time, but sometimes it will execute with system administrator privileges. Okay. And the crafting of these bytes will basically say when this subroutine is all done, when it executes a return statement, when it returns to the returns to the caller, it's not going to return to the caller. What it will return to is actually some of the byte pattern that you're overwriting with. Effectively, what the cracker is doing is to gain control over your program. By hacking a graphics file, an image file, okay, it can be a JPEG, GIF, or whatever PNG file. By hacking this particular file and make it not conform to the standard, there is a chance that a hacker can convince a subroutine not to return to the caller, not to crash, but to return, quote unquote, return to a place where it just overwrote. Okay. Now, because this content, which the program is intending to return to, is actually part of the file, the cracker can now specify certain types of code here to gain control of your computer. Is the general concept okay? I mean, I don't need you guys to actually write a Stack Overflow exploit in this class, but I just want you to kind of understand the kind of bad things that can happen when you make assumptions and say, oh, the standard specifies 512 bytes, everybody must be playing by the rules. No, some people will intentionally not to play by the rules to break the program. Do you think this might have happened in the past? That I'm just reporting something that has happened instead of something that is fictional that might happen. It has happened already, and many of you are probably too young to remember this. So what I'll do is I'm going to look it up. It's the GDI plus Windows Stack Overflow exploit. That might be sufficient to find it. The JPEG of death. Okay. GDI Plus Microsoft Security Bulletin. There we go. 2008, not too long ago, 7 years. Okay, so we'll go ahead and read just a little bit of what Microsoft itself has to say about this. Okay, this security update resolved 2 privately reported vulnerabilities in GDI. Exploitation of either of these will allow remote code execution if a user opens a specially crafted, in this case, a Windows Media Format image file. An attacker who successfully exploits these vulnerabilities could take complete control over an affected system. An attacker could then install programs, view, change, or delete data, or create new accounts with full user rights. In other words, pwn your computer, PWN, your computer. Now, the origin of that word is kind of interesting too. You can actually look up, why own is starting with a P. That tells you something about the hacker community. They might be really sharp and bright people, but they cannot spell. Some of them cannot. Okay, and the interesting part is also, what type of system is affected. Just look up this one here. This is a critical security update, which means do it now. Don't wait, because if you wait, your computer can be infected as a result. It affects Windows 2000 Surface Pack 4, which at the time was the latest Surface Pack. And this problem was reported when again? 2008. So some people are still running Windows 2000, which is a server infrastructure type of operating system. So it goes all the way back to 2000, up to the latest and greatest Vista at the time. It affects operating systems of a 10+ year span. Okay, about 10-year span. Can you imagine the? Okay, but why would anyone go look up an image file and get infected? Where do you think those image files will be? If someone who is malicious, who finds this out and go like, hey, I can actually make use of this to infect other computers. What do you think those corrupted images will be located?
Unknown place in the hacker place.
A hacker place? No, I wouldn't put it into a hacker place. Would you go to a hacker place, on the internet just check things out? No. Would you go to eBay? Craigslist? You wouldn't go to Craigslist or eBay to shop for things? I would. So I would just basically, look up the hottest, the most popular digital camera at the time, okay, and doctor an image, image file using an exploit like that one, and post an ad, somewhere on eBay. Well, I will get, hundreds of thousands of hits per day.
So just whenever the web browser views the image.
Exactly. This does not involve anything that you have to do other than going to the web page. And most browsers will not even ask you, right? Would you want to open this bitmap? Would you want to open that image? Because if that is what a browser would do, you'll be just clicking OK all day long. Every single web page is loaded with tens, if not hundreds, of images. So most browsers would just say, hey, here's an image. I'm going to load it up and display it. In the process of loading it, this kicks in, and it will silently take control over your computer.
And it doesn't matter what browser you use. This isn't like an Internet Explorer.
It has nothing to do with the browser, because this is a problem with the underlying libraries that is responsible to interpret a particular image file format. So it doesn't matter whether you're using IE or Firefox or Opera or anything, as long as it is running on top of any version of Windows from 2000 all the way up to 2008, Server 2008, your computer will be infected. Now, the good thing is this was reported privately. In other words, some security company, probably a virus checker company, discovered this particular problem and reported that to Microsoft and go like, hey, we got a problem here. What if a hacker is to discover this first? It becomes a zero-day exploit. Okay, what is a zero-day exploit? As opposed to a non-zero-day exploit. So a non-zero-day exploit would be someone who read about this stuff here and say, maybe some system out there is still not patched. So I'm going to create a virus or something that can infect a system based on reported and fixed problems, and hoping that some computers are not patched and will still get infected. But that would be a fairly small percentage. Okay? A zero-day exploit is something that has not been reported nor fixed. That is a zero-day exploit. So if a hacker, a cracker, is to find this particular security issue first and becomes a zero-day exploit, we can end up with a massive problem on hand, because you can end up with everything from Windows 2000 to Windows Server 2008 all infected, and the post-operation can be extremely messy, because there's no telling how those computers will be infected. If a rootkit is installed in those systems, you're looking at a really, really nasty problem from the perspective of Microsoft, because to remove a rootkit is really problematic. Just to find out that you have a rootkit on the system is difficult. Does anyone know what is a rootkit? Okay, I know I'm running a little bit over time, but since we're on this topic, even if you're not interested in programming whatsoever, because that's not your major, you should still understand some of these concepts. And I was about to look up rootkit. Okay, a rootkit, right here, Wikipedia. And we'll just read the first paragraph. Okay, the rest can be just technical details and stuff. A rootkit is a stealthy type of software, typically and almost always malicious, designed to hide the existence of certain processes or programs from normal methods of detection and enable continued privileged access to a computer, blah, 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 blah. Okay, so normally when you run a virus checker, how does it work? A virus checker goes through your entire file system, right? It goes through all the processes that are running, and it checks and say, okay, do I find a suspicious signature in this file? If so, it might be infected. I'll report it, or I'll just quarantine the file, do something about it. Okay? What if the infection, or what if the system is quote-unquote hacked to the point where the system utility to list files is already compromised? Then, when the virus checker is trying to say, okay, show me all the files in this folder, the utility to show all the files in this particular folder will intentionally hide certain file names. So at that point, your virus checker is neutered. Okay? Because what happens is it cannot even see the existence of certain files. How can you scan a file that you cannot see? You cannot. It can apply to also processes. A process is basically a program in execution. So if your computer is infected, there might be one or a few processes corresponding to the the program that's infecting your program. What if those processes cannot be shown? Your virus checker cannot tell. So a rootkit is much worse than a regular virus, because it can help to hide everything else. And the rootkit itself cannot be detected either, because it can hide itself. Okay? Because it's hacking all the utility programs of your operating system so that they are now blinded. Yep.
How can it be stopped? How can it be stopped?
How can it be stopped? The safest way is to reboot your computer with a live operating system. You can run Windows live from a CD or DVD. Okay, I cannot remember the name. Does anyone remember the name of that type of distribution of Windows?
I heard it like once. I've heard it like once.
It might be mentioned here, but you can. Okay, you actually, if you own a license of Windows, you can actually install Windows on a CD or a DVD, so you can actually run Windows from a DVD. So now you are running a different installation of Windows that is not infected. Then you can scan the hard drive for signs of a rootkit.
Is it like a boot CD or something?
It's a boot CD, but it's a special kind of boot CD because it's
you have
not.
to get if you want to install Windows without having it.
Okay, let me look it up. I can find that pretty quickly. Windows Slipstream Live. There's a name for it. I just cannot remember the name of that one. It's PE Builder. Pre-installed. That's it. Okay. So for those of you who want to look into this sort of thing, it's called a pre-installed environment. Okay. So if you look up Windows and pre-installed environment, that is what you need to look into, because that's the only sure way to detect a rootkit. Because by the time you run the suspicious or suspected system, the rootkit may be in effect already. If the rootkit is already in effect, then there's no way you can actually trust anything coming back from that operating system. So running a pre-installed environment that you can trust is the only way to do it. If a system is compromised already and you make a pre-installed environment out of it, it's too late already. So here's the other question. If you have Windows XP, which is a really old operating system, and you have the original install CD and you install it on the computer, and you hook it onto the internet, protected and unfixed, unpatched, how long would it take for someone from the internet to hack into that Windows XP system? Just give me an order of magnitude. Minutes. 3. So in less than the time you can actually go download all the patches and all the Surface packs, your computer is already infected. Before you can even bring up the firewall and all of the other useful stuff to protect your system, it's already infected.
Even if you go directly to the only website you visit is Windows to get
That's correct, because this is assuming that you don't have a firewall to block incoming connections. So if you don't block incoming connections, there are things out there on the internet that is probing every known IP addresses. As soon as your computer is up and you say, "Hey, I'm here," you get constant attacks already. If you put your computer behind a firewall, yes, then you just have to be sure that you go to the Microsoft website, download all the patches, all the Surface packs, and all the virus checkers, then you'll be okay. But if you don't put a firewall between your computer and the internet, you just hook it up to the internet directly, then it will only take minutes, 3 minutes or so, for Windows XP to be hacked. Yep.
That's how honeypots work, right?
Well, the concept of a honeypot is a system that is designed to be hacked, so you can backtrack who is doing it, how they're doing it, where they're doing it from, and so on and so forth. Yep. But a lot of times we have unintentional honeypots. it just happens, right? Yep.
Wasn't there something with Sony?
Yes, Sony has a fine tradition of upsetting consumers. So if you look up Sony and Rootkit, this is a funny one too. Not so funny if you got it, but okay. So Sony, not being a malicious hacking community, decides, hey, you know what? We hate people making copies of our audio CDs. Okay, so this is a while back, between 2005 and 2007. Okay, so what they did was they included a little bit of executable code on their audio CDs. So according to the standard of audio CDs, the standard allows that to happen. Okay, you can include some executable that the operating system can pick up and execute. Okay, so they included a rootkit on their audio CD. So we are not talking about something that you buy from Fry's and this will install blah blah blah, some kind of utility program. You are just going to a music store, get a traditional music CD, and you pop it into the CD tray of your computer and say, I just want to listen to this music when I'm working on my homework assignment, right? By doing that, it will install a rootkit onto your computer. The purpose of this rootkit is to monitor what you are doing with that audio CD without you knowing it, right? Because if it pops up a screen and say, would you like to install this software from Sony to monitor your use of this audio CD? Most people will say, no, heck no, right? So they don't bother to ask you, and it is installed in the form of a rootkit, which means it has means to hide itself from the rest of the system. And that's why it's called a rootkit, right? So if you look at this page here, it goes on and on and on to talk about the rootkit itself. The problem of this particular rootkit is poorly written. Okay, in other words, it will hide itself, but the rootkit itself is hackable as well. So other malicious software can now stack on top of the rootkit that Sony has installed on your computer. Okay, so you can kind of imagine the consequences of this whole fiasco on Sony. And then a few years after this, Sony decided on other things, like they originally supported a third-party operating system on a PSP game consoles, and then they decided to take that option away, and that generated a whole different type of fiasco, as far as Sony is concerned. But this is an interesting one from the security perspective. So did that answer your question?
Yeah.
Do you remember exactly what happened, or just kind of something happened?
I didn't really hear about this until I had another one of your classes before, and you brought this up
Yep.
in regards to security.
Yep. But this is a rootkit. It falls into the same category of all the rootkits that we just talked about. It is very stealthy, and can be very obnoxious. All right. Well, I think we're done for today's lecture. Say again? Oh, okay. So you guys just want to go buy a CD just to see what happens, right? I think they give you an idea of what CDs are involved here. So in Europe, BMG created a minor scandal in 2001 when they released this. I think it does give you a list of all the actual CDs involved. So if you can still buy one of those things, it's like a collection item now. Except there's a big label on it saying, "Do not put onto a CD tray of a computer." All right. Any other questions? So how do we go from arrays to Sony? Well, I remember exactly how we got there, but you all